let's actually start, pick up. Did Mr. Lillis make it this morning? No, maybe I should send him a message on Discord and be like, dude, bro, where are you? All right, so um, let's get to it. So let's pick up where we were right at the end last time, and then talk about a few other things based on some questions I've gotten. I want to make sure we're all kind of on the same page. Um, oops. So last time we were looking at the SIMD instructions. Good morning, Jack. Um, we're looking at SIMD instructions. So let's see. Let's open up. Let's see. We had this under projects. Where did I put the SIMD stuff? Oh, we never actually wrote it. That's right, because I had it on the. Oops. I think it was this one. Yeah, here we go. Okay. So let's just kind of recap what we had with SIMD. So you can take the floating point registers are actually 128 bits, but you can carve them up in different ways. So you can carve them up into all of the methods there listed. 2 doubles, 4 singles, 8 halves, or 16 bytes. For whatever reason that you might want to do that. The byte level stuff would be useful potentially if you're doing like image processing or something where you had like 1 byte per pixel or maybe 1 byte per color channel or something like that. So it's not outrageous to carve them up that way. And then the single, double, and half precision, right, just depends on what kind of floating point stuff you're up to. Um, and then here was sort of the picture as to how we could carve them up, right, into a single 128-bit thing or carved up into lanes within that of 2 doubles, 4 singles, 8 halves, and so on, right? Um, and the halves, by the way, are called, you'll notice they're called W for word, because the word length on, um, or no, I'm sorry. Um, well, that's interesting. Why did they use W there, but H up above? I wonder if that's a typo. Huh. Anyway, whatever. So we can carve these things up into however many lanes. And so last time, I think we were looking at my simple program to do. There he is. Did you catch another case of the dumb? Uh-huh. That's okay. I was dragging this morning too. Um, I don't know why I keep making myself teach at 8 o'clock in the morning. I know it's really, there ought to be a law against that or something. Huh? From home? Uh, yeah, I guess, right? I need to get like a green screen, but I'd have like the dog barking in the background and, uh, yeah. Yeah. All right, so yeah, so we just defined some floats here just because I was making a simple vector, and then I defined the other vector just in reverse order, no big deal. Um, and then we're going to load these things into some registers. And the one load instruction here that's a little different than before is to load stuff into the vectors, you use LD1. There is also LD2, 3, and 4. And as best as I can tell, basically what that does is just loads copies of things into the other ones. So like if, for example, you needed to load the same data into 4 different registers for whatever reason, then you'd use LD4. But anyway, okay, and so what data do I want to load here? Well, in this case, I want to load into my X registers, I need to load memory addresses, and then using that, I'm going to load in my vectors into, and I just picked 16 and 17 here for no good reasons. And then the dot whatever is telling me how am I slicing up my data into lanes? Well, I'm slicing it up into 4 single precision floats. Okay, in the 16 and 17 V registers. And where's the data coming from? It's coming from min memory, starting at wherever X0 and X1 are, or whatever contains them. Okay. Okay, great. And then we're going to multiply corresponding entries. Okay, so what will that do? Well, what's the dot product of 2 vectors? So if you've got 1, 2, 3, 4, and 4, 2, 3, 1, what's the dot product? You do 1 times 4 plus 2 times 3 plus 3 times 2 plus 1 times 4. Right, so you do each of those products, and that's what fmol is going to do, is each of the corresponding products, and then I just need to add up the answers. Yeah? Okay. And then I have to add them in 2 steps. So what's a little funky here is I'm going to take the things that are in V18 carved up into 4 lanes, right? That's where my products are. And I'm going to add them pairwise. So I'm going to take the first 2 lanes and the second 2 lanes and add them. Now I have 2 numbers, and those are going to go into the first 2 lanes of my destination register. The 3rd and 4th lane aren't used. Okay? But even though that's the case, you still have to put 4S on the destination, not 2S. Which I think is silly, but hey, that's the way what the assembler wants. So what the assembler wants is what the assembler gets. Oui ou non? Oui. Okay. And then this is why I really was annoyed by it, because the next step I want to add pairwise, but I'm only adding 2 things, namely 1 pair, and so there I do put 2S. Okay, so I'm sorry it is that way. I think it's silly, but again, I didn't make the assembler, so yeah. Okay, so this would add everybody up, and now sitting in register S0 would be our the computation for the dot product. Okay. All right. So and then basically let's just print the answer. Okay. Now the thing that we ran into the other day, right, is that how do you print a single precision? You have to first convert it to a double precision and then print that. Because printf wants it that way. So whatever. Okay. Okay, Gucci. All right, so let's program all this. So let me put this on half the screen so we can see it. And then let's get Jeannie on the other. I do want to come back to the inverse square root thing in a minute, but we'll do that in a moment. All right, and then so this is one reason I like desktop Ubuntu because it has snappy windows, so you can like easily half-size stuff. All right, so what do we need? Well, let's go back to the top here. Oops. All right, so we need our vector. All right, so let's see, we've got our data section, our text section, our main routine, okay? And in our data section, we need the two vectors. So we'll have vec1, which is uh, 1, 2, 3, and 4. Okay, and then vec2, let me just copy this. Vec2, I'm going to use the same thing, but I'm just going to put it in reverse order for sake of demonstration. Oops. Okay, so 4, 3, dang it, 2, and 1. Okay, and then this is vec2. Okay, so just whatever, there's my data. Okay, good. So we've got our data defined, and then what's our main routine going to do? Well, let's load in the data. Okay, so we need to do LDR x1 0, the pointer to vec1, the pointer to vec2. Okay, and then what? LD1. Let's go back to my directions here. LD1 V16.4 into 4 lanes coming from X0s as a pointer. Same thing with the other piece of data. Okay. All right, good. All right, now the next thing I'm going to do slightly different than the instructions that were on the slide because I want to reiterate proper handling of functions and subroutines. Okay, so if I want to write a subroutine to compute the dot product, then in C, for example, what I would be giving it would be an array, 2 arrays of 4 pieces of data each, right? The 2 vector registers. Okay, how does subroutine, well, and what kind of number am I returning from the dot product? Huh? Well, a scalar, but in this case, it would be what data type? Yeah, in this case, single precision, because that's just how we're going to compute everything. Okay. I think for all the assignments, I'm going to have you guys do double precision, and I'm doing single precision, but it's basically the same thing. Everywhere I have 4 S's, you're going to have 2 D's. Right, is the only real distinction here. Well, mostly. Okay. So parameters, how do parameters get passed to functions? They get passed in registers, or you pass pointers, or you pass things on the stack. Okay. So it's got to be some combination of that. And which one you have to do depends on what kind of data type, right? So if you're passing numbers back and forth or vectors, then you can put those things in registers because they fit into registers. if you want to pass strings or anything that's too big to fit into a register, then you either have to pass pointers, okay, which do fit into X registers, or you have to put things on the stack and know where it's going to be on the stack for the subroutine to pull it off the stack. Okay, you got to pick something, right? Just depends on the kind of data. All right, so what should a subroutine do? Well, a subroutine, and this is really going to be important when you guys are doing the recursion thing, right? What we are writing as a program is in a sense actually a subroutine, but it's a subroutine that's sort of the main routine. Okay, so what am I missing so far in my main program? Huh? Yeah, I got to set up my stack, right? And the first thing that I got to do is I've got to store the link register and the uh, frame pointer, and I need to put these somewhere on the stack. Okay, what comes at the end then? Well, at the very beginning of the program or subroutine, I have to store or push the X29 and X30 onto the stack so that the subroutine can finish cleanly and return back to the operating system. Okay, and then at the very, very end, I just have to pop those values off of the stack to restore the link register and the frame pointer to be what they were right when the program started, and that's how I'll give control back to the operating system. Okay, good. Now, technically speaking, anytime we make a subroutine, we should do that. We've gotten away with it in a few cases because our subroutines, like how do we branch to a subroutine? What do we do? What's the instruction? Branch and link, okay? So what does the link do? The L in branch and link. It says, okay, where am I right now? What line am I on? Or memory address, really, right? What's one instruction up from that, or down rather? Take that memory address and stick it in the link register. Okay, so the link register gets overwritten with something. Okay, now, if our subroutine, the subroutine itself does not also branch and link, then we don't have to do the store pair load pair at the beginning and end of the subroutine. Okay, and I don't think any of the subroutines that we've written so far have done that. Huh? Well, okay, let me back up. Any of the ones that I've written in class haven't needed to do that. Okay, now, yes, depending on how you structure something like string to int, then yes, it's possible that you have a subroutine itself branching to yet another subroutine. Okay. Um, okay. So in that situation, then your subroutines have to do the store pair load pair because otherwise you're not leaving the breadcrumbs as you go down to get yourself back up. Okay, which is why some of you guys are coming up with like bus errors, seg faults, or endless loops, or some combination of all of those. Okay. All right. So let's actually, for the sake of demonstration's sake, write this dot product thing as a proper subroutine. Okay. Um, so that we can see exactly how it's supposed to be for subroutines. Okay. So where if I'm passing parameters in registers, what's the sort of designated order in which you use them? Start at x0, or in the case of this function, since we're passing vectors, we should start with v0. Okay, and then where should the answer be coming out of this function? in something 0, okay? Now I say something 0 because what kind of register does the answer go for this dot product computation?
S0.
It's going to be in an S register because it's single precision, okay? So here we're going to pass two things in vectors registers V0 and V1. The subroutine is going to do something with them, and it's going to return the answer in S0. They're waiting for us. Okay, does that make sense? And if you had multiple parameters going in and out, which ones should you use? 0 through 7 is the convention, well, for the X registers. And then for the V registers, because they're sort of all equivalent, you would just go 0 through whatever. Okay, in our case, we only need 2 of them. If we were to do this dot product thing with double precision, I would actually need 4 vectors because I can only fit 2 coordinates in each V register, right? But in this case, I can do 4. Okay, so let me change this to V0 and V1, okay? Just so that I can stay with the convention of using the lowest end registers available. Okay, and then what I'm going to do is let's write a new routine. Okay, so the other thing I need to do is that, right? And let me actually save this before we get too far. Okay, so what I'm going to do right here is I'm going to say branch and link to dot product. Okay, and then we'll write the dot prod routine down below. Okay. And then now what am I going to do? I'll put the printing basically. So I'm going to add a string in here and make it print out the answer for us. And we'll put the printing part down there. But let's get the dot product computation part done first. Okay, so what do we got to do to compute the dot product? Huh? Yeah, we got to do some F-mulling. All right, so let's go over here and let's just check our instructions. Okay, so, but what's really the first thing I really truly should do? Yeah, store. Oops, sorry. And then at the very end, dang it, if I could type this morning, that would be fantastic. Okay, and then finally, return. Okay, now in this particular subroutine, we don't actually have to do that. And that's because this dot product routine is not going to call anything else. It's not going to branch and link. Okay, but what about if I put the printing inside the dot product routine? Then I would have to do that because I would be branching and linking to printf. And if I branch the link from, let's say I'm in routine A, and I branch and link to routine B, which branches and links to routine C, how do I get myself back up the chain if I only have one link register? I have to store previous values to the stack and pop them as I go back up the chain. Okay, does that make sense? Yeah, okay. So in fact, for sake of demonstration, let's put the printing inside the routine rather than outside it, just for giggles, okay? Okay, so first thing, we need to compute the actual dot product. So let's do fmul, and then in this case, I'm changing the numbers. So let me put my products in V2, and then of course my, right, so this is the one, since I'm renumbering the registers, okay, from before, right, I've got fmol, so I'm going to multiply corresponding entries from V0 and V1 and put those answers in V2. Okay, is that all right? Sure. Mm-hmm. Okay. Yeah, so if before you do the store pair, yeah, probably that would be a good idea because then you don't have to do any thinking, right? Because otherwise, like, if you push this onto the stack before you pop the other values off, well, okay, I should be clear. You're not really popping them off, you're just loading them, right? They're still there, right? Um, so yeah, I would do that because otherwise, what you would have to do is say, okay, load from stack pointer plus 16 and stack pointer plus whatever, rather than just stack pointer plus whatever, right? You'd have to think, oh, I just expanded the stack by 16 bytes here. So how far I need to go up the stack to get to my data has now changed from when I went into the routine. Okay, does the question make sense to the rest of you? Yeah, Michael? Yeah, you could do that too, right? Is pass the pointer and then just load off the stack using that pointer, because then you just know the absolute address to it rather than thinking of it as relative to the stack pointer. Okay. Um, yeah, that would also work, right? Or, um, well, yeah, okay. And if it's something like a string, that's probably pretty big. Or let's say you have some weird compound data type, like, and we haven't actually talked about this, but um, does Java have, what do you call it in Java where you put like, well, I guess it'd be a class, right? Where you have like, let's say, class customer, and then within that would be like customer first name, customer last name, which would be strings, and then say customer address and customer phone number and blah, 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 blah. You'd make that a class. Okay. Well, so in C, there's an object called a struct, which is kind of a class, but not really. And that's something that Dr. McCartan Lim. So, how many of you guys are going to take the operating systems class next semester? Yeah. Okay. So he's definitely asked me to talk a little bit about structs on the assembly level because that'll be useful for you guys in operating systems. So, yeah. Um, in fact, I think it may be the case in the future that we make this class a prereq for something like operating systems because, it's not like you're going to be sitting and doing assembly all day long, but you need to know some of it, right? Um, Now, this does beg the question, and it kind of dawned on me this weekend. I was like, oh, crap. I don't know what kind of assembly he's going to have you guys looking at, right? Because if he's doing operating systems, and he's going to have you guys look at both parts of the Windows and Linux kernels, it's probably x86. And you know what I really don't want to have to start teaching is x86 assembly because it's a nightmare. ARM is so clean, it's so luxurious. Yeah. Anyway, okay, so we've got our fmol, Gucci. What else do we need? We need to do our adding pairs. So let's all right, so f add pair, and where are we going to take this stuff to? So we're taking v2.4s, adding pairwise with v2.4s, and where are we going to put the answer? Let's put it in v1.4s, right? Now, I'm nuking the vector in the process, but that's okay. Okay, and then finally, fhead pair v0.2s, or sorry, v1.2s is my source, and I'm putting that answer in S0. Okay? Yes. Nope. You can totally do that. Right. So source register and a destination register can be the same. And I think the reason that you can do that is like when you do an operation like this, there's the the floating point unit, I think, has sort of hidden registers inside of it. So you put in like the two things get copied into these hidden registers. The operation takes place on those hidden registers, and then there's a write back phase. So it's not directly operating on the register level. And that's something that we'll talk about hopefully when we get into the architecture stuff, um, which maybe Thursday, maybe next week. We'll kind of see. I still want to do um, GPIO probably on Thursday. Okay. Oh, by the way, I've got some really good news. What's the really, really good news? Huh? Yes, sort of. Asterisk. It's even better news than that. Uh, it's not that good, right? There's no final. Forget it. Okay. Huh? Because I don't feel like it. um, yeah. Say less. So no final. We'll just keep going with the projects and polish those off. So no final. Yeah. Any complaints? Now who's not here today? Huh? Huh? Yeah, where is Evan? That's a good question. Um, and Walter's not here either. And Pruitt. So if you guys see them, you tell them that McKinney was so pissed about how many people were missing this morning that he threatened to make the final even harder. Oh, you're okay. Pruitt's online, right? Because Pruitt is, I think, under lockdown right now. Um, yeah. So, all right. Question? Ah, yes. Thank you. Okay. So, one of the things that talking with Will, we discovered, to my surprise, frankly, um, so subroutines are not obligated to preserve registers x0 through x7. Okay, there are some of the integer registers that are obliged to be preserved by subroutines. Now, one of the things that we'll notice, and this really surprised me, is that the vector registers are not obligated to be preserved by printf. Now, why on earth would printf need floating point registers? I have no idea. Okay, other than if it's using them because it's a pile of registers just to use. Okay, so what this means is that if I'm going to branch to printf right here, what's in S0 coming out of printf will be potentially nuked. Okay, so I should store that in and then push it onto the stack and pop it off of the stack after I print to take that into account. Okay, now I think for this, am I going to put the print inside or outside? What did we decide? Outside, inside. Okay, let's put it outside. Okay, so in this case, am I done with the dot product computation? Yes. Okay. And all I have to do then is load back and return. Okay. Now, because this subroutine, like I want to reiterate this subroutine does not itself call another subroutine. I don't actually need the store pair load pair here. Okay. But what about if in the middle of this I did something like branch and link to foo? Then I would need it. Okay. So what's the cover your butt trick? It's better to have it there when it's not necessary than to not have it when it is. Then you do need it because you're branching and linking to printf, which is, foo, printf, who cares? It's a routine, right? Okay, so we've computed the dot product. The answer is sitting in x0. Okay, now I need to have a string, okay, for printing the output. And let's just make it the dot product is that, okay? We're printing a float, right? The dot product is whatever. Good? And then if I go down here, I need to set myself up for printing. So what's got to go in X0? To print. Address of the format string, which I called outstring. And what's got to go in S0? Nothing. What goes in D0? S0 converted, right? So why don't we actually put the conversion down here in the subroutine, right? So what's the conversion? Yeah, F convert. Okay, so we're actually returning using D0 rather than S0. Okay, and that way, what's sitting right here in D0, do we have to actually move anything? No, it's already there. Okay, so I need to branch and link to printf. Okay, good? Yeah? All right, well, let's assemble it and make sure that we didn't screw something up. Hopefully. All right. Well, let me make sure I saved it. All right, so I called this SIMD. All right, so AS, I'm going to go ahead and do it with the debugging stuff. That's good. Also good. Okay, that's not the correct dot product. What should the dot product be? Should be 30. Okay, why the hell did we get 21? Uh-huh. Oh, right. Okay, so I just put it in the wrong order. So then I want 4848. Oh, okay. So this should be the one at the bottom. There. Oops. That's definitely not what I want. Okay, so it was correct. I just had the data in the wrong order. Wait a minute. What was it? 1 times 4 plus 2 times 3 plus 3 times 2 plus, yeah, that's right, 20, not 30. What am I smoking? Okay. Okay, so 20, right? 0.00. Oh, by the way, you notice that the default is 6 decimal digits. What about if I want more? Well, how did we deal with this when we were taking input strings? Yeah, let's just throw a number in front. So I'll go up to 18 because that's sort of the limit of a double. Okay, that should have worked. Is it dot? Okay. Uh, yeah, there we go. Okay, my bad. Forgot the dot. Okay, now obviously that many digits is superfluous, but that might be kind of handy for the floating point fun with floats assignment, right? Because this way you can see, kind of when the numbers start actually looking different. Okay. All right, so let's run this through the GNU debugger because we want to see what Will observed about the V registers. Um, okay, so let's just do it, right? GDB, um, SIMD, break main. Oh, let me fix the window width a little bit here. Okay, so break main, run, and then let's actually break. Um, okay, so what I just did there was I put a second breakpoint in at the dot prod, and then just hit continue, and that takes me all the way until the next breakpoint, if any, right? So I don't have to step through the whole bloody program. Okay. All right. So let's look at. Actually, you know what? Let me start over. Or no, no, I want to run. Yes. Okay. All right. So what I want to look at is what's inside vector v0. Okay. Well, it's a bunch of gobbledygook, right? So what are we looking for here that tells us what we've got?
The second line at the far right.
Yeah, second line at the far right is sort of the view of it that we want to see. Okay, so because what I see there, S equals 3F80 blah blah blah, that's 1, comma 40, and then it wraps to the next line, that's 2, then 3, then 4. Okay. All right, and let's see actually if it will do it. I'm not sure if this syntax will work in GDB, but let's try it. Nope. Okay, that's not valid. What I want to know is how to carve it up a little bit more so that we don't see all this gobbledygook, right? But if we look, like say right here, right, what do we see? Well, we see our numbers 1, 2, 3, and 4, right, in sort of individual little lanes. Okay, does that make sense? Okay, and then if we do the same thing for V1, we should see exactly the same data, just in reverse order, because that's the vector I picked. And yeah, same data, just reverse order, because that's what I picked. Great, okay. All right, so then if we step, okay, the next instruction would do the fmol. So let's look at, and I put the destination stuff here in V2. Okay, so let's look at what we've got there. Well, what's 1 times 4 and 4 times 1, the guys on either end, is just 4, which is right there. And then 2 times 3 and 3 times 2 is 6, which is this one and that one, the 4, 0, C0, blah, blah, blah. Okay, so that kind of makes sense, right? Yeah? Okay, then when we start to add it, okay, so this would be the add pair instruction just happened. And here I put the pair added into V1, and what do we see? Well, I added pairwise, so what am I going to get? I'm going to get 10 and 10, right? And do you guys buy that this is 10 and 10? Actually, it looks like 10, 10, 10, and 10, which is interesting. Yeah, I'm not sure why it does that, but whatever. The extra 10 and 10 we don't care about, because what are we going to do next? We'll just add the first two, and I put this into S0. So if we look at V0, right, what are we looking at? It's really just that part, okay, which is 20. Okay, and then if I look at S0, which is really part of V0, excuse me, there I've got it, okay. All right, so there I've got um, my number, yeah, okay. All right, does that make sense? Yeah, good. All right, so let's step a bit more here. All right, popping this thing off the stack, we return. Okay, now we're about to print. Okay, so let's look at, say, V0. Oops. Right, it's still got the number in it. Okay, it's really S0 that, so let me just restrict our attention to that, right? Or I'm sorry, D0. Because what did we do at the end of the floating, I mean the dot product routine? We converted it from a single to a double because that's what printf wants for whatever reason. Okay, so there's our number, right? We've got the number 20. By the way, you see that second set of brackets there where it says F equals U equals S equals? Okay, what's going on there? F is for float. U is for unsigned. That's if you pretended it was an int. And S would be signed if you pretended it was an int. Okay. Right, so if I took the hex number 4034 blah 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 and pretended it was an int, then it would be worth, 4 gajillion whatever whatever whatever. Okay. I'm not actually sure why they thought it was useful to go ahead and put it in there like that, but hey, whatever, we got it. But what it means though is that you could use floating point registers to store integer data, right? If you really wanted to. And then they're just registers, right? Okay. Okay, so what's about to happen? Let's go to, let's print. Okay, it printed, and now look what's in D0 after we printed. Is that what it was before? Well, certainly not. It's garbage. Now, it's very interesting garbage, because look at it in hex. That's kind of a neat pattern. Okay, so what happened? What did printf do? It did something to my D registers. Okay, it did something to D0. And in fact, while we're at it, let's look at the V registers. All right, that one left alone, interestingly enough. That one looks good. I don't think I put anything in V3. Oh no, wait, that's almost the numbers that I had. But it's not quite though, because look, there's some stuff at junk at the end. Right? Okay, so it went messing with my registers. All right. Okay, lesson learned. So if you're gonna have floating point things and you want to branch to routines, You better save that stuff to the stack before you branch because it's not going to be there when you come back. So, okay, great. That was surprising. Like, it's not surprising that it did this with the integer registers, but why printf needs floating point registers? No clue, right? Um, it must accelerate it or something like that. And I mean, because if you think about it, right, think back to like the 70s or 80s. Processors didn't have floating point units back then. And if they did, they were an extra chip, right? Which you may or may not have had. So, um, I mean, nowadays you can assume that you have a floating point unit safely because basically every processor since I think, the last time the processors didn't have the floating point units on them for sure were the 486s. Pentiums and up had the floating point units built in, which was one of the selling points for the Pentium, and also one of its downfalls. If you guys know about that, the Pentium FDiv bug. So the floating point division thing had a very obscure bug that like only would crop up one every 30 million. Like the odds of you finding this bug were incredibly small. Um, and it was a math professor at a small liberal arts college who found it. So anyway, I think it was at Lynchburg College. So the way the floating point unit it included a lookup table, and it had I think 5 out of the 1,000 values in the lookup table were wrong. They were zeros when they should have been twos or something, and it was enough to screw it up that you would notice. And he was doing like number theory research, so he started seeing weird values, and that's what tipped him off that something was up. Okay, anyway. Okay, so that's great for SIMD. Let's quit this and let me close Avu. We've got this saved. I also want to go back to let's go back to the float or the all right, so project close, project open. I wanted to look at the inverse square root thing again. And then okay, did a little bit of research. In particular, um, I think I overstated myself a little bit last time when we talked about, let me go back on the PowerPoint here. FRSQRTS. It does not do the entire Newton's method. It only does part of it. Okay, which we discovered. Thanks, Will, for cracking the whip on me. Okay, so when I say down there at the bottom that FRSQRTS does the standard Newton iteration for the inverse square root to improve the estimate, it does not. It does part of it. Okay, so what I'm going to do is let's see if I can do this. Well, I'll just stay on the pie. So let's talk Newton's method for a minute, especially for those of you guys who haven't taken any calculus or it's been a while. So let me go to Wolfram Online. Okay, because I want to use some Mathematica to demonstrate something. Okay. So I'm going to make a new notebook. And what we are doing when we use Newton's method is a numerical technique for solving an equation. Okay. And the equation that I want to solve in the case of inverse square roots is I want to solve the equation 1 over x squared equals a for some value of a. Okay, so if I want to, for example, do this 1 over the square root of 2, what I'm looking for is the solution to 1 over x squared equals 2. Right? Algebraically, the answer would be 1 over the square root of 2, right? Because we're not morons. Okay, but I need to have the equation in that form to think about this for Newton's method. Okay, so what I'm going to do is I'm going to define a function. And I'm going to define it as 1 over x squared minus a. So basically, I'm just moving everything in my equation to one side. So what I'm really solving is that thing equals 0. Okay, I'm finding a root. Yeah? Okay, good. Now, for the sake of demonstration, let me put the specific value that we were interested in for computation's sake of 2. Okay, yeah, Will. No, it's a square. Okay, good question, right? Because, so, well, okay, here's why, right? That's why, right? If 1 over x squared equals a, then x equals 1 over the square root of a, which is what we actually want to compute, right? So it's a little backwards, I'll grant, okay? All right, so let's plot this thing, this function, huh? Okay, if I plot this function from 0 to 2, okay, this is what I get, right? So where is the answer that I'm looking for? It's right there, right? 1 over the square root of 2 is like 0.707, blah, blah, blah. Well, okay, there she is. Okay, so that's what I'm looking for. But I don't know where that is, right? So what are the two built-in functions to ARM that do this sort of stuff? What's the E function? FRSQRT-E. What's the E stand for? Estimate. It produces a pretty good guess, but it's only a guess. Okay, how did I compute the estimate when we demoed this last week? I did it with that magic number voodoo, right? It also produced an estimate. It wasn't as good as the built-in estimate, but for the 90s it was great because there was no built-in estimate. That's all you had was this trick. Okay, so that produces a guess, and then it's how we take the guess and then get to a better guess that's what makes Newton's method. Okay, so let's make a guess. Let's make a really terrible guess. Okay, that maybe not quite so terrible. Let's say we guessed 1. Okay, that the square root 1 over the square root of 2, we're guessing 1, which is a bad estimate, but it's not that far off from 0.7, is it? Okay, so if I guess the number 1, right, what can I do? I'm going to draw a tangent line to my curve, okay? And what is the equation of the tangent line? Well, it's f at a point plus f prime at that point times x minus that point. Right? Okay, so that's just the slope of a tangent line, rise over run. Okay? And then what I'm going to do is I'm going to plot that. Sorry, this is really slow. And I'm going to change my plots here to go from 0.5 to 1.5 since we know that the answer is somewhere on that interval in between. Okay, and then what I'm going to do is I'm going to show these two plots together. Okay, so this will take a minute to run. Okay, so let me actually back this up to 0.25 for reasons that'll become clear in a moment. Well, okay, let me do 0.4. I'm just trying to make the picture look good at this point. Okay, so is that okay? All right, so what I've got here is I've got the curve, and I'm trying to find where the curve intersects the x-axis. Good? Okay, now, what I've drawn is I've drawn a tangent line. It's a straight line, right? So it's not very hard to do algebra involving a straight line. Where does the straight line intersect the x-axis? I could figure that out, right? And it's just a little bit shy of 0.6. Okay, now I've overshot my target, but I also started with a really crappy guess of 1. Okay, so what about if I had picked a better guess to start with? So let me do, for example, let's do, say, 0.8. And draw the same picture. Okay, now I'm writing my tangent line, and where does it cross the x-axis? Well, it's pretty dang close to the true answer, right? Is this, where this intersection point, is that better than the guess that I had to begin with? So I started with 0.8, and where does it intersect? Well, I'm not sure. Actually, let's find it. Okay, is that better than 0.8 to our problem? Yeah, a little bit, not tons, right? Or to borrow a line from, have any of you guys seen the HBO miniseries Chernobyl? It's like 3.4 Rontgen, not great, not terrible. No? Okay, whatever. But it's a better estimate, right, than what I started with. So what about if I take that 0.688 and I replace the 0.8 with that 0.688? This would produce a new estimate that, guess what, will be even better. Yeah? You guys trust me? Trust me, I'm a doctor? Oops. So I'm going to replace that with 0.688. Rerun it. Resolve it. Ah, that's getting better. Right? Okay, so what I'm using here is a technique called Newton's method. And the magic for Newton's method is the following. The equation for how you solve for that tangent line is this. You do y, your guess, minus f of y divided by f prime of y. It would help if I could type this morning. And that gives us this expression. Okay, now let me simplify this a little bit. Okay, And what I'm going to do is I'm going to refactor it a little bit as the following. I'm going to refactor it as y times 3 halves minus y over 2 times, yeah, here, well, yeah. Okay, so sorry, because this would be, all right, let me factor in a y first. So this would be 3 halves minus y squared, right? Okay, which is the same as y times um, 3 minus 2y squared over 2. Okay, so I'm sort of sorting these things out. Okay, now what I want you to do is I want you to look at it in this form here. Okay, compare that to the code that was in the Quake 3 example, right? It had a 3 halves and stuff in there. Okay, all right, so let's look at it in this form right here. Okay, and I'm going to take that one step further, and I'm going to write this as y times 3 minus 2y times y divided by 2. Okay, so what the the step instruction does on the ARM is it does this, 3 minus x times y over 2. Okay, so what you have to give it is you'd have to say, this would be FRSQRTS, destination register. Well, and you can do this with S's also, S or D, right? And what it would do is it would take D1 and D2 and replace them with X and Y in my formula there. It would multiply them, it would subtract the product from 3, and it would divide everything by 2. Okay? So, if I want to implement the line up above, I have to actually do 3 operations. I have to take y and compute 2y. Well, that's easy. Just double it, right? I then have to use the step tool thing, and then I need to multiply that answer by y again. Okay, so what I would need to do is let me scroll down a little bit here. Okay, so to implement it, I would have to do the following. Suppose D0 has my guess, okay, that I produced using the estimation step or with the magic trick, okay? Then I would need to do fmol. Well, first I need to load 2, okay? Then I'm going to do fmol okay? Then I need to do FRSQRTS. Let's say my destination is D3, whatever. And then I'm going to do D0 and D2. Okay, so D3 now has 3 minus D0 times D2 over 2. Okay, what do I need to multiply that by? Okay, so now I've computed this part of it. That's sitting in D0. What do I have to do? I need to multiply that by my guess. Where's my guess? My initial guess. D D0. Okay. And that would, so what does this do? It takes a guess you already have and it improves it. Okay. So if I wanted to get this really accurate, what would I do? Yeah, Michael's making the motion. Just do it again and again and again. Put this in a loop, right? Each time you do it, it improves the accuracy of your guess. So if you do it 10 times, you're going to have a pretty dang good estimate. Okay, now, in Quake 3, how many times did he do this sort of procedure? Just once, okay? That was enough for the accuracy of the 3D computations that he was doing in the game, right? But in the code, he actually had a second iteration there. He just commented it out because he found it wasn't necessary for the accuracy of the game. It was good enough with a single iteration, and that sped things up. Okay. Now, if you were doing some sort of like serious physics computation, you might want to take that further. Okay. The other thing is, now, how many of you guys are in the numerical analysis class? Have you taken that or no? Numerical analysis? No. Okay. Have you guys talked about other numerical solving techniques other than Newton, like Hawley or more general techniques? Yeah. Okay. So you can improve on this, but what's the trade-off? You have to know more calculus. Okay. And those methods are kind of right. They're more computationally expensive and more complicated to write down. And the question is it worth it in terms of runtime? Maybe yes, maybe no. Right. That just depends. Okay. Did you guys? And the last thing before we quit, did you guys see my the link I sent about sort of an example of a recursive program? Yeah. Okay. That's going to be really helpful when you guys write your Fibonacci routine. What's two things about that program that you need to change? He uses X19 the way we're using X29. Okay. Big. That's not a huge deal. The other thing is, what is his example doing? It's computing Fibonacci's. And what are you guys going to compute? Tribonacci's. What's the difference? Right. The Tribonacci's, you add the next term is the sum of the three previous rather than the two previous. Same idea. Okay. But it would be kind of lame if I gave you an example of Fibonacci numbers and then asked you to write a program to compute Fibonacci numbers. Right. So, all right. See you guys on Thursday. Hang on one second.